this computer. Okay, we now be recording for 110, and I will be talking to you. I'll be sharing my screen with you and showing you notes as well as PowerPoints. So if for an example here, I can share screen, and here's the notes, if you can see that. These are the notes that I always encourage students to print up ahead of time, because this is what I talk from. If I scroll down, can you see these here?
Yeah. Yes.
So if I scroll down, you'll see the end of page 1, and now page 2, and I'll scroll down to page 3, and then down to the last page, page 4. There's usually 3 to 4 pages of notes in each unit. This is unit 1, and we'll be spending 3 weeks this week and 2 more weeks on unit 1. Oh, hello, another joiner. Great. Anna Woods, good to see you. All right. Okay, and then what also I'm going to be showing you is, of course, the PowerPoint presentation that goes along with the notes, and you can see the PowerPoint. Now, I don't ever print this up. I mean, this you'll have to kill some trees, okay? So don't do that. Always have the notes, though, printed up ahead of time, laying on your desk beside you while you're listening to the Zoom session, because that's what I'm going to be talking directly from, okay? So here goes. Here's our notes, starting out, acoustics. And if you read with me, you'll see some strange, weird words, sinusoids, frequency, period, wavelength, speed of sound, sound fields, resonance, impedance. At the end of 2 weeks from now, you'll be able to know exactly what those things are. Okay, but we'll get to it bit by bit. In this course, we will cover the physical properties of sound. I mean, if you're going to be working in the field and you're going to be fitting hearing aids on people, oh great, we've got another person here, great. If you're going to be fitting hearing aids on people, you have to know what sound is, okay? You have to know what decibels are. You have to know what frequencies are. What's bass? What's treble? What do they look like? What's the difference between the words, the sounds? And then think of the most important sound for anybody to hear, and that's speech. And what is speech made out of? And how does speech differ from noise, like traffic, background babble? You know, that's the biggest complaint of hearing aid wearers is background noise. Because hearing aids are dumb. I mean, they just amplify. They don't know what the listener wants to hear. So you'll be learning a lot about that. Now, in 120, are you taking 120 as well this semester?
I am.
That's in about 2 hours from now. I'll be teaching you that too. Okay? And acoustics and anatomy are married in this course. We'll be referring to them back and forth, which is why I'm glad you're taking 120 anatomy as well, because the 2 courses are like the 2 pillars that hold the whole foundation of the field. Your acoustics and your anatomy courses are they're theory, okay? They're all notes and PowerPoints. And there's no hands-on, you're not doing anything, you're not coming to Springfield to handle anything, but these are your 2 real pillar theory courses. And in a first semester, it's really important to be taking these courses together. I think I'm really glad you are. One thing too, as I said, did you guys all get the email letter that I had sent with the link to this Zoom session?
Yeah.
Okay, and in that letter I said too, never try to watch a Zoom session on a phone. I can see that you aren't. You're sitting at homes or in a place looking at a computer, which is good. Because some of the PowerPoints, I'll show you what I'm saying. Here, I'll go to show PowerPoint here, and you'll see the PowerPoints they have details on them. Look at this. I mean, how are you going to see all of that on a phone? You know what I'm saying? So you need a screen of some size. Well, I'll come back to that in just a sec here. Let's go back to our notes. In this course, we will be covering physical properties of sound, acoustics. Now, look at this weird sentence here. or that I've highlighted. Physically, sound is a propagated change in the density of an elastic medium. Oy, weird. Okay, let's talk about what that is. If a tree fell in the woods and no one was there to hear it, would there be a sound? And the answer is yeah, there'd be a sound. Because what is sound? A propagated, meaning forced, something made it happen, okay? Change in the density of what? Air. The molecules in air, okay? A propagated, meaning forced, it was made to happen, like hitting a tuning fork, ding, or plucking a guitar string, or talking, okay? So a propagated change in the density of the molecules of air. And an elastic medium doesn't mean rubber bands, it's just a medium where molecules can be moved. So a propagated change in the density of an elastic medium. Okay, that's the physics way of saying it. So back to share a screen. Look at our notes here. Next sentence. Psychological perception of sound is called psychoacoustics. Okay, and that's what we are going to be studying in the second half of this class, is psychoacoustics after your midterm. So we break down the course into two halves. Unit 1, 2, and 3 are covering the physics of sound. Intensity, complex sounds, high pitches, low pitches, the decibel, all of that stuff. And then you have a midterm exam halfway through the course. And then you take psychoacoustics. And psychoacoustics is the perception of sound. If you doubled the frequency, did your pitch perception double? If I doubled the decibels, does my loudness perception double? Not necessarily. Our brain changes sound a bit. Sound, we're not machines. We're human beings. And we, like dogs hear differently than humans. Cats hear differently from dogs. So being mammals, we have different brains, different ear systems, and so we favor the pickup of some sounds, and we don't favor the pickup of other sounds. Okay? And that perception is called psychoacoustics. And we'll be learning about that as well, the second half. So when you hear acoustics, you'll always see acoustics / psychoacoustics. Acoustics is physical acoustics of sound, physics, and psychoacoustics is perception of sound. And then that gives us a good basis to cover. In fact, I think what I can do is I can share a screen here, and what I will do is actually show you the, here, I'll blow this guy up here. This is what we're covering. So look at it this way. Unit 1 today. Here's the PowerPoint in red. There's the notes in blue. Next week, same unit, same topic. Next week after that, same unit, same topic. Then we go to Unit 2. Can you see this here? Intensity and the decibel. And you'll see notes and a PowerPoint for that. We'll spend 2 weeks on that. Then we'll go to Unit 3 and talk about complex sounds and speech. We'll spend 2 weeks on that. Then you'll have your midterm right after Unit 3. And notice Unit 4, psychoacoustics. And Unit 4, the PowerPoint for psychoacoustics. And then a new topic in psychoacoustics, Unit 5. Once again, notes and PowerPoint for Unit 5. And then notes and PowerPoint for Unit 6. And then the very last unit of the course is non-electronic modifications of hearing aids. In other words, what does the shape of hearing aids do to the sound of hearing aids? And that should do it for 110. So that's kind of what I wanted to impart to you. So okay, here we go. Psychologically or perceptually, sound is an auditory experience, the act of hearing, psychoacoustics. Anatomy and physiology of the ear is covered in anatomy, 120. And anatomy sits right in between the physics of sound and your perception of sound. Anatomy is kind of the human being or the organism through which sound has to go to get to the brain. And that's what we're going to be covering in 120. We'll be covering the outer ear, the middle ear, the inner ear, and all the pieces and parts of the ear and how they work. It's kind of neat. You're going to like anatomy. So here we go. We delve into a little bit of the physics. Now here I'm going to show you a PowerPoint slide, and you can see this here. In fact, I might make it really big and just blow it up here. Can everybody see that? Good. This is talking about light waves, not sound, light. So let's look at the wave on the very top. Do you see this wave? How it's really, see where my cursor is? It's really blah, blah, and then all of a sudden it starts to get more bumps, and then more bumps, and more bumps, and okay? On the left is fairly low frequency, and in the middle would be middle frequency, and on the right is high frequency. So when you think about frequency, that just means how many times something happens per unit of time. So look at AM radio on the left. That's got long radio waves. See, radio waves are like light waves, but you can't see them. And then you have shortwave radio. And then you get television and FM. And then you get microwaves, you know, the ones that are in your kitchens, microwaves. And then you start getting other kinds of waves that are getting smaller, and then infrared. And then look at this, visible light, the light that we can see with our eyes, okay? And then you get higher frequency, and it's ultraviolet. And then you get into X-rays and gamma rays, okay? Now let me just explain to you, I'll show you another picture. Here's visible light. Here's what I'm showing you is just this. See this area in purple and pink and red? I'm blowing that up. Red is a low frequency light wave. Blue is a high frequency light wave. So within the visual range of light, okay, red is the lowest frequency and blue is the highest frequency. Well, all right. Let's just stop sharing here and we'll say, sound ain't light. Okay? We're not opticians. Light can travel through outer space. Light can shine from the moon. Light can shine from the sun. How did it get here? Didn't travel through an elastic medium. It didn't travel through molecules because space doesn't have any molecules. Outer space has nothing. So light can travel through nothing, okay? Sound can't. If you were on the moon and I was on the moon, standing 3 feet away from you, I can yell till the cows come home. You're not going to hear a word I'm saying. How come? Because there's no air on the moon, okay? Light can go through space. Sound can't. Sound has to travel through water. Whales can hear each other, dolphins can hear each other, or air. Humans can hear each other, dogs can hear each other, or through metal, like railroad tracks. If you put your ear to the railroad track, you'll hear the train coming, okay? Sound needs something to travel through. Light doesn't. Here's another thing about the difference between light and sound. Light travels, get this, 186,000 miles per second. That's 6 trillion miles an hour. If you did the math, light travels 6 trillion miles an hour. Sound travels 766 miles an hour. You get the difference? Sound is a slowpoke compared to light. That's why you see the lightning first in a storm, and later on you hear the thunder. Sound travels way slower than light. And by the way, nothing can go faster than the speed of light. There is nothing. You cannot go faster than the speed of light. How long did it take light to go from the moon to the earth? 3 seconds. How long does it take light to travel from the sun to the earth? 8 minutes. It takes 8 minutes. The sun is 93 million miles away from Earth. The light from the sun takes 8 minutes to get here. The light from the nearest star takes 4 years to get here. So the fastest, if we had a spaceship and could travel to the nearest star, it would take you 4 years to get there at the speed of light. Just FYI. It's got nothing to do with hearing, but when you know who you're not, you get a better idea of who you are. And sound ain't light. So let's talk about sound. Let's get to know our buddy. We'll move from this slide to this slide. Here's sound. Here's a picture of a tuning fork. You can see a tuning fork here, like this U-shaped thing with a handle. Someone struck the tuning fork, and it's making sound waves. And look at the sound waves. You've got squeezing and then separating. Squeezing, separating. Squeezing. So the squeezing, separating, squeezing, that's the propagated changes in the density of an elastic medium that I was talking about earlier. Okay? Because otherwise, the molecules in air are just randomly, they're moving around, and that's called Brownian motion. It's in your notes, but I'll take you there in just a second. That's Brownian motion. When you make a sound, you are propagating a change in the density of the elastic medium. You're all of a sudden, you're making some order to the random Brownian movement. You're making squeezing and separating, squeezing and separating, squeeze. And look what we call those. Those are called compression or condensation for the squeezing and rarefaction for the spreading. And one squeeze and one spread is one sound wave. Let's look at it. Here's another picture showing you the same thing. Here's a sound source in the center, and then here's a spread and a squeeze, a spread and a squeeze. You see that? Sound radiates in all directions like a sphere. It just goes out from the center, and it goes out in squeezing separations, squeezing separations. Again, the squeezing is called condensation or compression, either one, and the separation is called rarefaction. Compression, rarefaction. And here's a picture out of your textbook that shows you compression, rarefaction, compression, rarefaction, and look at the sound wave below. See the sound wave below, how we draw it up and then down, up and down, up and down. The up portion of a sound wave represents the condensation or compressions. The down portion of a sound wave represents the rarefaction. And one compression and one rarefaction is called one cycle, one wavelength. Okay? So one sound wavelength. And we'll follow my cursor. It starts at 0 here, goes up to 90 degrees, then to 180, then down to 270, and at 360. You just did a 360. In other words, if you take this bottom part and you swivel it back over to here, you'll have a circle. So just like a circle has 360 degrees, so does a sound wave. 0 degrees, 90 degrees, 180, 270, 360. Now you're back where you started from again. So when we talk about sound waves, we draw them like they go up and down. But their sound doesn't really go up and down. If sound went up and down, you and I'd be going like this, listening to each other. Okay? Sound waves don't go up and down. We draw sound waves like they are up and down because it's easier than drawing this. It's easier than drawing the top. That's why we draw sound waves the way they are. We draw sound waves up and down because we're on a piece of paper with a pen. Okay? And a piece of paper just has 2 dimensions, length and width. Sound travels in 3 dimensions, of course. Okay, so sound waves travel through out like a sphere, but we draw them up and down because it's easier. Now I'm going to take this and we'll go to the notes and let's see where we are. Let's just read now. Brownian motion, the random movement of molecules in air or water or metal. Some medium. Those are called media. Okay, the thing through which sound travels is called a medium. Okay, so the medium can be air, it can be water, it can be metal. Now, as heat is increased, the molecules tend to move faster anyway, and so sound waves tend to travel a little faster through heat than they do through frigid cold air. But no, don't worry about that. Propagation. Strike a tuning fork. Something has to cause or propagate an abrupt change in the random Brownian motion. The fork tines movement, the fork, okay, the thing that I could, the tuning fork that wiggles back and forth, those are the tines. The fork, the things of the tuning fork, okay, they move back and forth past the center due to inertia until elastic force cancels out the inertia. Now, don't freak. Don't, when you hear the word elastic, there's two things you're going to hear a lot in this course. Elasticity or elastic does not mean rubber bands. Okay? Elasticity in this course means stiffness. The other thing that complements elasticity is called mass. Mass is like the weight, the density, the heaviness. So when you think of weight or density or heaviness, think mass. When you think of stiffness, think elasticity. And I know it kind of runs against the core because when you think of elastic bands, you think, and elastic bands aren't very stiff. Well, forget about elastic bands. This is physics. So in physics, elasticity refers to the stiffness of an object. In physics, elasticity or mass refers to like the density or the weight of an object. Hang on, I'm going to close the door behind me. The better half has just come home and she doesn't need to hear me barking into the computer screen. So, okay, here we go. All right, so share screen again. Back to our notes. All right. You can read this just for fun. Elasticity, the ability to recover from being distorted. Oh, yeah, all right, well, take a look at that. Elasticity, the ability to recover from being distorted. That's stiffness. Okay? In other words, the stiffness is the opposite of being compliant. Something is really compliant, it's not very stiff. Hey, I'll give you an example. A bouncer at a bar, his attitude is pretty stiff. Okay, you throw a beer in his face, his attitude's going to even get worse. He's going to get even more pissed off. Okay, so just think about elasticity as the stiffness of an object through which sound's got to travel. Density is like the mass of an object through which sound has to travel. And I'll just tell you one thing right here. It's interesting. Mass resonates with low frequencies. What comes through, you're sitting in your apartment and you're trying to listen to the TV, the news, and the neighbors upstairs are playing loud music. What comes through the ceiling? The drums and the bass guitar. Because the ceiling has mass, and what's going to resonate with mass is low frequencies. On the high frequencies, like the cymbals, aren't going to go through the ceiling. Highs resonate with stiffness. Okay, we'll be talking more about that later on, and we'll be talking about resonance more later on as well. For now, though, let's follow our notes and move on down. So here, when you're reading this, you can kind of read this for your own, thing. But what I want you to do is put a star here where it says sound waves are series of squeezed, condensed, and then spread out rarefacted molecules. Moving on. Sound waves, longitudinal versus transverse. Those are, put a star by that section too. Longitudinal versus transverse. Transverse waves or longitudinal waves. You got two kinds of sound waves, okay? Or not two kinds of sound waves, two kinds of waves. Water waves are transverse. Water waves go up and down, and the direction moves. But the up and down is perpendicular to the direction in which the wave is moving. Okay, think about that. Transverse. Water waves. The waves of the ocean or lake, they're coming toward you, but they're also going up and down. And the up and down is perpendicular to the direction in which the wave is traveling. Not so with sound waves. Sound waves are longitudinal. So let's look at two waves here to help you get that idea. Okay, here we are. The top wave is longitudinal. You've got a squeezing and separating, and the wave is moving this way to the right. The bottom is actually showing you a transverse wave because the wave is going up and down and the direction is moving to the right, okay? Or to the left, whichever, it doesn't matter. Sound waves are longitudinal waves. The squeezing and separating is happening in the same direction as the motion, as the wave is going. So you've got squeezing, separating, and that's happening along the same plane as the direction of the wave in which it's going. Water waves ain't true. Water waves go up and down, and that's perpendicular to the direction in which they're moving, not parallel. Okay, so we draw sound waves as if they are transverse. We draw these longitudinal waves, we draw them like this. Why? Because it's easier. Okay, but again, to underline, sound waves don't go up and down. We draw them like that because it's easier. Good. So, whoops, where's my notes? Here we go, back to the notes. Transverse waves are like waves on water. Molecular motion is perpendicular to the direction of the wave. Longitudinal waves are how sound travels. The molecular motion is in the same direction as the wave. Okay? We draw sound waves like up and down bumps because it's much easier than drawing down lots of molecules bunched together and spread apart. Now, can you see why watching Zoom sessions in a course like this is way better than sitting there reading your book and trying to figure it all out? Okay? All right? To cuss a little bit, it beats the shit out of sitting there reading. Okay? It's important to watch the Zoom sessions because everything is in here. I'm cheating. What I'm doing is I'm taking the book, because I've read your books 1,000 times, and I'm making cheat sheets. I'm making, those notes are like condensed, what do you call it, summaries of what's covered in your books. The books are great to have for your continuing education in this field. Always keep your books. Always read them. When you're a practitioner, when you become an HIS, you're going to have those books sitting on your shelf. You may refer to them very, very often to get clarification of things. So the books are important. Don't underestimate that. But what I'm telling you is that in order to pass a course like this, your quizzes, your midterms, your final exams rely a lot on these Zoom sessions. There's a lot, I really reiterate that because there's a lot of students in past semesters that just didn't quite get it. Oh, are we supposed to watch those? It's kind of like, duh. Oh, did I ever show you the new cup I got? Look at this. Look at a hippy-dippy looking van, eh? I live on the Pacific Northwest. It's hippy-dippy country out here. All right. We'll show you a part of your notes that I'm going to write FNO, freak not out, because it's kind of, you're going to look at the bottom of your notes here going, oh my God, what is this stuff here? It's this right here, what I'm highlighting, right there. So I can write here FNO, freak not out, or for nerds only. Okay, I'm never going to ask this on anything. I just am giving it to you so you can see what the next picture is that I'm going to show you. Okay, see how a circle has 360 degrees, 0 to 90 to 180 to 270, back to 0 again, to 360. Now look at the wave. There's a sound wave drawn, okay? 0, 90, 180, 270, 360. Okay, if you took this part here and you swiveled it around to go underneath here, you'd have a round thing. You see my cursor?
Mm-hmm.
But it wouldn't be totally like these. See how these are rounded? Whereas these show kind of a point. And that's the point of that whole bottom of the page, is just to show you that actually the condensations are tightest right in the middle. It's not solid black here and then solid white here. It's tight black here, and then only here is it really white. And then it's tight black here, and then only here is it really white. That's all that's showing you, okay? So this sound wave here isn't really all that accurate. They should have drawn this sound wave here so it looked more like these, like that, okay? Or like this. Here's a speaker. Yeah, just check this out. Here's a speaker, and here's another speaker. Now the top speaker is vibrating, and it's making a low frequency sound, a bass sound. Look at how big its white and black areas are. So we draw the sound wave like, okay? The down portion represents the white, rarefacted. The up portion represents the dense, the compressed condensation. And then here representing again the white over here. And then the up over here representing this black here. Now look at the bottom speaker. It's making a higher pitched sound, a higher frequency. It's making a treble sound, like the birds. And so its compression rarefactions are smaller, aren't they? Okay? Now time, follow my cursor. If this is 1 second, okay, that didn't change from the top to the bottom speaker, but what did change was the number of compressions and rarefactions per second. So the top speaker's making a low-pitched sound, the bottom speaker's making a higher-pitched sound. The more compression rarefactions you have per second, the higher the frequency, the higher the pitch, okay? The fewer wavelengths you have per second, the lower the pitch. That's really important to understand. This isn't so important to understand. That's why I said this is really for nerds only. I'll never ask you about it, but there it is. All that bottom stuff that's shaded here is just to tell you that sound waves actually should be drawn more like a point, because sound waves actually look like this more, and therefore this wave here isn't totally accurate. But enough on that. Let's move on. Look at that. We've already done page 1. Okay, we're moving on now to page 2 in your notes. Chill pill. Coffee time. There you go. How's it going so far? Okay? Cool.
Yeah.
It's just great. He said in his best Scottish. All righty then. Oh, hi, let's go on to the top of page 2. When you're looking at the top of page 2, there's 2 ways to represent sound. Okay? One way is the sound waves that we've shown you. Waveforms. It's called a waveform, like we've been talking about. It's got 2 labeled axes, time and amplitude. It's easy to see sound as it changes over time, but it's hard to show the individual frequencies very well. In other words, decreased width shows increased frequency. Oh yeah, look at that, HZ. HZ stands for Hertz. H-E-R-T. We say in Canada Z. You say south of the 49th Z. Hertz. You ever heard of Hertz rent-a-car? Okay, Hertz. It really hurts. Okay, H-E-R-T-Z. Hertz means cycles per second. Hertz means how many cycles did you have? Look at the sound wave here. Pretend this sound wave took 1 second. From the left here to the right is 1 second, okay? How many cycles do you see? I see about 3. You see 3 bumps here. Okay, so that would be 3 cycles per second. I guess that would be about 3 hertz. Okay, hertz is number of cycles per second. And what's a cycle? 1 condensation, 1 rarefaction. What's another way to say it? 360 degrees. Starting at here to 180 to 360 is 1 cycle. How many cycles per second? Okay, that's sound waves. And the height of the wave, how tall you drew it, would show the amplitude. How tall is it? Okay, so the number of cycles per second shows the frequency, or the hertz. The height of the wave would show the amplitude, the decibels. How loud is it? Okay, good. Let's move on here. Oh, here's another picture showing you 360 degrees of a sound wave. If this time on the bottom was 1 second, you'd see 1 cycle in that second. That would be 1 hertz. Okay? Here's a cycle of sound that went the opposite way. Its first part was rarefacted, and the second part was condensed. This wave here started as condensed and then rarefacted. This one was the opposite. It doesn't mean anything. It's okay. It still has 360 degrees, doesn't it? Okay? So that's a single cycle. It's kind of like the picture I drew you here. This cycle began as a rarefacted. This cycle happened to begin as a condensed. Doesn't matter. Either way, 360 degrees is 1 cycle. 1 cycle. Even this one, that's got 360 degrees too. Because it started at this, went to here, and then back to where it started. That's got 360 degrees too. It just happened to start at 90 degrees. This one here started at 180 degrees. This one here started at 0 degrees. It doesn't mean they're not nice waves, they're just different. So here you're looking at 3 dimensions of sound. So these are all sound waves. This is all the first way to represent sound. Okay, sound waves. Here's 2 tones with the same starting phase. They all started at 0 phase. But look at this one here. It's got more bumps, more cycles than this one does. So if this is all time, see how they're showing you time on the horizontal, amplitude or pressure on the vertical, just call this amplitude, okay, or loudness, whatever. Okay, these 2 tones here, they differ only in frequency. They don't differ in amplitude because their height is the same. Okay, this is the same loudness. They just differ in frequency. Look at the middle 2 waves. The middle 2 waves, they have the same frequency, the same hertz, and they have the same amplitude. They're just as tall as each other. It's just that one's beginning a little bit earlier than this one. So these 2 waves differ in terms of time. The top 2 waves differ in terms of frequency. Okay, the middle 2 waves differ in terms of time. And the bottom 2 waves, they've got the same frequency, don't they? The same amount of bumps. And they started at the same time. How do they differ?
Amplitude.
Good, correct. So sound takes place over 3 dimensions: frequency, intensity, time. Okay? Yet we only have a flat piece of paper with 2 dimensions. So we have to have 2 different ways of describing sound, because sound waves don't include all of it at the same time. I've got to draw different ways to show it all. Okay, so sounds can differ in terms of frequency, they can differ in terms of intensity, or they can differ in terms of time. Very good. Now, here's another picture showing you the same thing. Same thing as this one. Okay, this is from your textbook. Now, I don't know if it's figure 210 anymore. Martin's textbook. Martin is one of your authors in this course. Frederick Martin, and I believe it's something Clark. Martin and Clark. Are you holding that up? Yeah, let's see that.
Yeah.
That's good. All right, great. Yeah. Introduction to Audiology. That book comes out every year in a new edition. Those guys must be making thousands in royalties. At any rate, I used to use that book when I was studying audiology years ago. Every year or every second year, it comes out as a new edition. I don't have your latest edition, but they're all just about the same. So if my figure says 210, yours might read 211, whatever. Big deal, okay? The other textbook you're going to use is called, I believe it's called Hearing Science Fundamentals by Lass and Woodford. That is a really good book. If I had to choose between the 2 books, I'd choose that one. That's a really good book because it tells you about sound in ways that you can read so easily. It's like it's written in English. So I really like that book. Martin's is okay. He's pretty good in some things, but not so good in others. Anyway, but they're both good. I put them both in as textbooks because they complement each other well. At any rate, as you're reading your textbooks, your readings in Martin, be sure to keep up with your readings in Lass and Woodford, because that's a pretty good textbook. So at any rate, there you have it. Here, let's see what other lie I can tell you. Okay, here at the top. So the top 2 waves, how do they differ? Amplitude. Consider the time to be the same, okay? If it's a second, a half a second, whatever it is. Whenever they're talking frequency, the time unit is always a second, okay? How many cycles per second? Not minute, not hour, just how many cycles per second? So 60 hertz means you had 60 cycles per second. 100 hertz, 100 cycles per second. So here you go. These 2 waves differ not in hertz, not in cycles per second, they differ in amplitude. These 2 differ in frequency. They're the same in amplitude, they're just different in the number of cycles per second. See, and time is always on the horizontal. Memorize this. In a sound wave, in waveforms, and even in the word. Here, let's go to here, just to bug you. Go to the very top. Look at this word here. Sinusoid. Sinusoid. Where does that word come from? Sinus. Your sinuses. Your sinuses are curved passageways behind your nose. In Latin, sinus means curved. Okay? A sinusoidal road is a road with lots of hairpin curves. Your sinuses are bent and folded over each other. Sinusoids are sound waves. Okay, so when you see the word sinusoid, just think sound waves. I remember when studying it, I got really confused. And what I want to do is I always want to explain in a way that I wish someone had explained to me. That's what I'm trying to do, so that you don't get bummed out and freaked out, or what the hell is sinusoid? Oh, that's a sound wave. Okay? How many sinusoids did you see per second? How many sound waves did you see per second? All right, good. All right. Back to where we were. Okay, that's that word there. Go down, down. All right. And I'll show you the PowerPoint here. We're doing well. This is good. The bottom 2 waves differ in terms of time or phase. Okay? Phase means time. Time means phase. All right. So these bottom two these bottom two waves, they have the same amplitude, they have the same frequency, but you know what? Look at this. They cancel each other out, don't they? If you took this wave here, you mixed it with this wave here, you'd have the sound of one hand clapping, silence. Because they're canceling each other out. Their rarefactions and compressions are completely canceling each other out. Anyway, the top two waves differ in terms of amplitude, the middle two differ in terms of frequency, or hertz, capital H, small z, and the bottom two waves differ in terms of time, or phase. And if this happened in an auditorium, the bottom two waves, you would have a dead spot in the auditorium, because the top wave and the bottom wave bouncing off of the wall, let's say, if they occurred in opposite phases, you'd get a dead spot in the room. That's why acoustical engineers are hired, to make sure you don't get phase cancellations in an auditorium. We'll get to more of that later. Okay. And here's a nice thing here too, and we can kind of almost finish with this slide. Look at this one for today. Here we go. I hate this black thing. I wish it would go away. Go away. Thank you. Oh, okay. Sound waves. Period versus wavelength. Period is the time it took to have one cycle. Follow my cursor. How long did that take on your watch? How long? How long in time did that take? That's period. Okay? Wavelength is the actual physical length of the wave in feet. How big, how long is the wave? How big is it? Okay, when you think of a low frequency wave, it's got length. I'm going to show you a picture of that. Here, let's go way back to almost to our original slide here, and I'll show you what I mean. Here, how long was one of these rarefactions and compressions? How big was it in feet? How long was it? Let me tell you something. Low frequency sounds have a long compression and a long rarefaction. In fact, if a sound is about the frequency of my voice being about this pitch, the sound waves are about 125 hertz, 125 cycles. Get this now. This is 125 hertz is about 9 or 10 feet long. One compression is about 4.5 feet, and one rarefaction is about 4.5 feet. Mind you, now, if you take a bird chirping, really high-pitched, those waves are really short. One compression, one rarefaction is really, really short. Now let's tie this to the animal kingdom. Think about elephants. Large animals, large ears. Did you know that elephants emit very low frequency sounds? We can't even hear them. They're kind of like, and those waves, those sound waves are so long, they're like longer than a house. And they bend around objects because they're so long. That's how elephants can track each other's movements miles apart. People in helicopters or planes can see trains of elephants walking in perfect parallel. And zoologists only figured out recently how they did that. They are communicating with low frequency sounds, and low frequencies bend around things, over rocks and trees and down into the next valley, because they're so long. Now let's go to bats, the animal kingdom. Let's talk about bats. You're blind as a bat. How do bats catch insects at night? They're flying and they're eating insects. How the hell do they do that? Because they emit high frequency sounds way above our hearing. We can't hear it. And those high frequency sound waves are so short. Each condensation and rarefaction is so short. Those waves don't bend. They bounce. They bounce off of things. So they use them like radar. They bounce off of the fly, and they know where the fly is by how the sound bounced off of it. And that's how they catch flies, even though they can't see. Okay? So I hope we're putting together a whole picture of sound here. Low frequencies, high frequencies. Sounds can differ in amplitude, they can differ in frequency, they can differ in time. And remember, frequency is the number of cycles per second. And we call that hertz. Capital H, little z. It's the definition of cycles per second. When you think of the word frequency, that's a good word. What's the frequency of my footsteps? Well, you always have to have a time unit, don't you? Oh, look what I got. Someone gave these to me. Here, I'll use real feet. Okay. What's the frequency of my footsteps? Well, you have to have a time unit. You mean per minute? You mean per second? Okay. So frequency just means the number of times something happens per unit of time. And in sound, that unit is seconds. How many cycles took place per second? Okay? With bass, you have fewer cycles per second. Okay? So with bass, you have a longer period. Let's go to the slide again. With bass, so the bottom sound would be a bass sound. It has a longer period and a longer wavelength. Period is, it takes one cycle of sound, follow me here, one cycle of sound, would take a longer time to occur, and AND, and its physical wavelength would be longer. High frequency sound on the top, its period is shorter, and its wavelength is shorter. Always remember, period is the number of cycles per second. I know that's wrong. Period is the time it took for one cycle to occur, one condensation, one rarefaction, the time it took for 0 to 360 degrees, in other words. And wavelength complements period. Wavelength is how physically long was the sound wave. So period is the time it took to occur. How long did one sound wave, how long did one cycle take to occur? And wavelength is the physical length of one cycle of sound. Very important to hold those distinctions in mind, okay? I'm going to pull this out here, and we will look at our notes. All right. Now, the spectrum is a different way. And a spectrum, if I have it here, and we'll talk way more about a spectrum next week and the week after and the week after that. But here's a picture of a spectrum. Okay? It's showing you all kinds of sound waves. Look at this. 100 hertz, 200 hertz. See how frequency is Hz? Okay? So it's showing you a whole bunch of different tones of different frequencies. And it's not showing you the sound waves at all. Screw that. It's not even showing you that at all. And here's amplitude. So it's showing you frequency, amplitude. Whereas a sound wave is showing you time and amplitude. Time and amplitude. So wavelength or sound wave or sinusoid, these are all the same. They're showing you amplitude over time. Whereas a spectrum is showing you frequency and amplitude. But enough on that. Here's an analogy. The two ways to show sound. Think of sound waves as a loaf of bread from this end to this end. A spectrum is going, taking a slice of the bread and turning it sideways so you can see the raisins. Okay? A spectrum is doesn't have time in it. A spectrum doesn't have time at all. It's just a slice of the sound wave. It's taking a knife and going, and then it's turning the wave this way to see what's in it. Is it this frequency and this frequency and this frequency? Hopefully it isn't just this one. No, I'm just teasing. Okay. So anyway, there's lots. We have time. We've got 2 more weeks to cover this section. So if I were you, I would just be I would review what you've got, and I would look at this section for next week, because we're going to start next week here. Look at this. Okay, we talked about amplitude, frequency, and phase or time. Note the different amplitudes, and that all this, see this grayed area here? This gray area here refers to this slide and this slide. Okay, that's what that grayed out area in your notes refers to. And then next week we're going to go on and talk a lot more about frequency and period. You see where I'm highlighting? And then we're going to be talking about frequency and wavelength. So that's really what we're covering next week in this course with a vengeance. We're covering frequency and period. And right after the word period, please put, where you can see it here, the time it took to complete one cycle. Right where I'm here, period. The time, and point at your watch, the time it takes to complete one cycle. And wavelength is the physical length of the wave. So we'll be covering those two things big time next week. All right, there we go. I think that's good for today. Yeah. All righty then. Any questions? So if I imagine, who knows, you'll come up with them. No worries. You can reach me by email, okay? And I don't know if you have my email, but I'll give it to you. It is Venemat, V as in Victor, E-N-E-M-A-T for Ted, all one word, Venemat @otc.edu. Plain and simple, plain and simple. Cool. So if you have any questions that way, give me a shout. I'll be happy to try and answer you. If you have an emergency and you need to give me a phone call, I can be reached at my landline is best. My cell charges me because I'm in another country. My landline phone is 604, that's the area code, 492-1013. Okay, that's my landline phone number. Use that as a last measure, but I don't think you'll, I think we'll be fine anyway. Should try email first, of course. If I check my OTC emails every day, every stinking day. So I work part-time for OTC. I work about 19 and a half hours a week for OTC. And then I teach full-time at another program here. It's another HIS program in British Columbia, Canada, at Douglas College. That too is that's a partly online and partly face-to-face program. Students have to come to school once a week. So they can't live more than about 100 miles away because they got to go to school. They got to be in class once a week. So it's kind of a hybrid. OTC has more online component, but at any rate, the acoustics course is the same for both colleges. Your anatomy course is identical for both colleges. In the summer, when you take hearing disorders, that's identical for both colleges. So I'm teaching the same courses at both. Anyway, it's been a slice. It's been. We'll see you next week at this time, but actually I'll be seeing you in about an hour from now in 1:20. So I'm going to have a, what do you call it? Take a walk. I'm going to water the plants. It's kind of dry outside. Take a stretch, grab a coffee, and I'll come back and see you in a bit, okay?
Thank you.
Adios, amigos.
Bye.
All right. Live long and prosper. All right. Now I can stop recording.